Okay, hello everyone. In this video, we are going to discuss about Laplace transform of unit step function and corresponding numericals. In our last class, we have been discussed about integration of Laplace transform and its corresponding numericals, this one and this one in detail. This class, we are going to discuss Laplace transform of unit step function. Okay, so let's start. The unit step function, which is also known as half-side function or half-side unit step function, is defined as ut minus a. Here u is the small u, okay? Ut minus a is equal to 0 when t less than a and 1 when t greater than a. Here a is the constant, okay? Here a is constant. Now we are going to represent graphically this function or unit step function. So along x-axis we consider t and along y-axis we considered u t minus a. And here you can see that less than a, suppose along x-axis this point is your t equal to a. Less than t equal to a, the value of u t minus a is 0. Okay. Greater than t minus a onwards, the value of u t minus a is 1. This is the value 1. So below a it is 1, sorry, below a it is 0 and above a it is 1. So this is the typical representation, graphical representation of unit step function. Now we are going to go for Laplace transform of unit step function. Laplace transform of u t minus a or unit step function will be equal to, in generalized way we can write 0 to infinity e to the power minus st into that function. Here we consider the unit step function, that is your u t minus a dt. Here u t minus a is 0 from 0 to a, or below a this value is 0 and above a it is 1. So I am going to segregate this limit as 0 to a, then a to infinite. 0 to a e to the power minus st, and this value is 0 into dt, plus a to infinite e to the power minus st, and this value above a is 1 dt. So here 0 is there, means this term will be 0, plus integration of this one with respect to t, e to the power s minus st dt, integration with respect to t, means here minus a is constant, so integration will be e to the power minus st by minus s a to infinite. Now I am going to substitute the limits. Here minus 1 by s taken outside, so infinite if I am going to put, it will be e to the power minus infinite minus e to the power a, I will be put over here. Instead of t, it will be e to the minus sa. We know that e to the power minus infinity is your 0. So here minus minus plus, we found e to the power minus sa by s. So Laplace transform of unitary function u t minus a equal to e to the power minus sa by s. Remember, it always required for the different numericals. Now we are going to go for a simple example or numerical, that if unit step function is represented as u t minus 3, then find its Laplace transform. So here if I am going to compare this u t minus 3 with u t minus a, here a is nothing but 3. So Laplace transform of u t minus 3 will be equal to e to the power, here you can see minus sa by s. So e to the minus sa or as we can write itself, 3s by s is your answer. Okay, now we are going to go for another numerical which is somewhat interesting, that is your express the following function in terms of unit step function and then find out Laplace transform. The given function is your 8 when t less than 2, 0 when t greater than equal to 2. So our first task is that we have to represent this function as unit step function. Okay, how it is? See, given function is this one. That implies f of t can be written as, here 8 can be written as 8 plus 0 and 0 can be written as 8 minus 8. Okay, so this one for t less than 2, this value is t greater than 2. Okay, now here I taken 8 common from these two terms. If I will taken 8 common, that means it will be 8 plus 0 when t less than 0 less than 2, and here minus 8 when t greater than 2, greater than equal to 2. That means if I am going to add this 8 with this one, I am going to 8 plus 0. If I am going to add 8 with this term, then we can find 8 minus 8. So this can be written as 8 plus 0 t less than 2 minus 8 t greater than equal to 2. That implies ft equal to 8, and here I am going to take minus 8 common from these two terms. So minus 8, if I am going to common from this 0, it will be 0, and here I am going to take minus common from this term, then it will be 1. So minus 8 taken common from these two terms, so minus 8, 0 t less than 2, 1 t greater than equal to 2. That implies f of t equal to 8 minus 8 into this one is nothing but your ut minus 2. Because if I am going to consider this one only, here a is nothing but 1. Okay, sorry, here a is nothing but your 2. You just compare this one with this one. Here 0 1, 0 when t less than a, 1 when t greater than. Here 0 less than 2 and 1 less than, sorry, 1 when t greater than equal to 2. If I am going to draw this one, only this one, then what it will be? It will be like this. This side is your t, this side is your u t minus 2, and this point is your 2, and this one is your 1. Okay, so this is nothing but ut minus 2. Now we are going to take the Laplace transform both the sides. So Laplace transform of f of t will be equal to Laplace transform of this one. So Laplace transform of 8 minus Laplace transform of this one. Laplace transform of 8. 8 is the constant taken outside. That means Laplace transform of 1 will be nothing but 1 by s. So Laplace transform of 8 is nothing but 8 by s minus, here 8 also constant taken outside, Laplace transform of ut minus a. Here a is nothing but your 2. Here we found that Laplace transform of ut minus a is your nothing but e to the power minus sa by s. So here instead of a we have to put 2. So the answer will be e to the power minus 2s by s. So finally the answer will be 8 by s 1 minus e to the power minus 2s is your answer. Okay. Now we are going to go for application of unit step function. First we have to draw the graph of ut minus a minus ut minus b. Here b is greater than a. Okay. So we know that only ut minus a is nothing but before a the value is 0, after a the value is 1. This one. This graph represents the ut minus a. As I told that here b greater than a, so ut minus b is nothing but, here b will be there, greater than a means the point will be here, and before b this value ut minus b is 0, and after b this is 1. Okay, So we have to draw this one ut minus a minus ut minus b. So if I am going to subtract from this graph to this graph, only this portion will be there. So you just subtract this graph from this graph, then what we are going to found we found only this portion. Okay, so in between a and b the graph will be remaining and other will be subtract from this graph. So we found that ut minus a minus ut minus b will be equal to this one, this much. Okay, below a is 0, after b also 0. So this graph is nothing but representation of ut minus a minus ut minus b. This is required for different numericals. So here one numerical which can be solved by this concept. Okay, how it is: express the given function in terms of unitary step function, then find the Laplace transform. Here given function is your f of t equal to e when in between a to b and 0 t greater than b. So this f of t value will be e when t in between a to b and 0 when t greater than b. So how we are going to solve it? Here you can see that given function is your f of t equal to this much. F of t, here I taken e common from these two terms, so we can found 1 0 1 in between a to b, 1 when t in between a to b and 0 when t greater than b. So this is nothing but your u t minus a minus u t minus b, right? So this will be equal to e into this much is nothing but u t minus a minus u t minus b. Now we are going to consider the Laplace transform. So Laplace transform of f of t will be equal to Laplace transform of this much e into u t minus a minus u t minus b. So E constant taken outside, Laplace transform of ut minus a minus ut minus b. We know that for ut minus a Laplace transform, this will be e to the power minus as by s. Laplace transform of ut minus b will be e to the power minus bs by s. This will be the answer. So here we are going to stop our today's class. In our next class, we are going to discuss second shifting theorem and its corresponding numericals. Okay. Actually, second shifting theorem is linked to unit step function. So in next class, we are going to discuss in detail about second shifting theorem. Already first shifting theorem we have been discussed. This one. First shifting theorem already we have been discussed. I'm going to show you. This one. This one is your first shifting theorem or first translational property or shifting property. And this one is your second shifting theorem that we are going to discuss in our next class and corresponding numericals. So thank you so much for watching this video. Thank you.